Hey guys, today we're going to take a look at the geometric distribution. So the primary difference between geometric distribution versus previous distributions we've looked at is that they have a waiting time. Okay, so what I mean by this is there's no set number of trials. We're just going to continue to go until we succeed. Okay, so like before, this is a distribution with independent trials. Oops, let me switch to independent. Okay, so each trial is not affected by previous trials, but there is no n value this time. Okay, there's no set number of trials. Okay, so an example of this is playing Monopoly. When you're stuck in jail, you have to roll doubles in order to get out. Now, there's the $50 rule, but we're just going to ignore that. So we're going to figure out the probability distribution for getting out of jail by rolling doubles. Okay, so first of all, let's see. So one of the things you have to remember, one of the easiest mistakes on this, is that your x value or your random value or random variable actually represents the number of failures before success. So there is a 0 here. So this first one is a 0 because that would be you succeed on your first roll. So there were no failures. Okay. So we can have 0, we can have 1, 2, 3, 4, 5, and we could theoretically continue on to infinity. Obviously, that's extremely unlikely, but you could theoretically continue to roll and never actually get doubles. So the probability of just rolling once and getting doubles right away is just going to be 1 in 6, because probability of rolling doubles is 1 in 6. Okay, so getting it on the first try, 1 in 6, which is going to be 0.17. Okay. Now the probability of failing once, here let me roll so you can see the 1, sort of. Okay, the probability of failing once and then succeeding, so you've got 5 out of 6 because you failed, and there's 5 out of 6 ways to fail by rolling doubles. Remember the success is actually 6 out of 36, but I'm reducing these fractions. So this would actually be 30 out of 36, but I'm reducing those. So anyway, we have the 5, 6, and then when we roll the second time, that's when we're going to succeed. So there's 1 in 6 ways of that happening. And so this is going to give us 0.14. Okay? Next, we will fail twice and then succeed. So what we're going to do is we're going to say, all right, well then we'd have 5, 6, but that's going to happen twice. So I'm going to square it. Okay, we're going to fail twice, and then we succeed. Okay, and this time we'll get 0.12. Now you could be using, you could continue to use fractions obviously, but as you go, the fractions are going to get messier and messier. So I'm just using decimals for practical reasons at this point. Anyway, so you can see the pattern. You can just see, so we say for every time we fail, we're just going to multiply by another 5, 6. So this one's going to be 5 to the 6 to the power 3. And then times that 1, 6 again for the success. So we get 0.10, and then we'll have 5, 6 to the power of 4 times 1, 6, which gives us 0.08. Okay, and we would just go on and on and on like this. You get the idea here. So. Okay, and that just gets bigger and bigger and bigger. I didn't actually figure this one out ahead of time, but we can say, well, it'd be like 625 out of 3125, something like that. Anyway, it doesn't really matter. What matters is just this pattern. So I'm actually going to jump ahead a little bit here because you can probably figure out the actual equation at this point. So the probability of having x failures, okay, probability of x failures before success is going to be equal to q to the power of x times p. Okay, and just like before, the Q is the probability of failure. A little bit here. Okay, the P, oh my goodness, why is this not working? P is probability of success. And then finally, our X is the number of trials, or actually the number of failed trials, we'll say. Failed trials. Okay, so there we go. So that's our probability for this question. So if I were to graph this distribution, okay, graph it, we'll have 0.1, 0.2, and then we'll do 0, 1, 2, 3, 4. I'm just going to stop at 4. And we would have something about there, and then we go down to about there. It's not going to be perfect, but it's okay. 1 about there. 3 is about there. 4 is going to be about there. So that's obviously not drawn perfectly, but close enough. The idea is you can see that this is going to get smaller and smaller and smaller, and it would actually continue on theoretically forever. Okay, and so this should actually be the x-axis there. The 0 should actually be an asymptote. Because of course there's always a possibility of failing 10,000 times before finally rolling doubles. It's just extremely unlikely. Okay. So we're going to look at the expected value. How many times do we expect to roll to fail before we finally succeed? So what we're going to do here, I'm not going to actually use the correct formula off the bat because I want you to see something. We're going to use the expected value formula that we used in the very first lesson of this unit. So this was where we took each outcome and we multiply it by the probability of that outcome. And then we just add it to the next outcome multiplied by the probability of that outcome. And that would just go on and on forever. So let's do what we have here. So we have 0 times 0.17 plus 1 times 0.14 plus 2 times 0.12 plus 3 times 0.10 plus 4 times 0.08, and then this would just go on and on and on. Okay, so we're going to add up what we have as an approximation. Okay, so if we add up what we have there, that will actually give us 0.654. Okay, now what's important about this is that this is a terrible approximation. Okay, so that is not a good answer. Okay, so that's not a good answer, and that's because there's no n value here. So there is no n. So for this to be a good approximation, you would have to go on for a very long time. You would have to calculate this on, into the thousands before you're getting anything even remotely close. Okay, so I'm just going to show you now the actual formula that you would use, and then we'll try it again and see how close we got with that estimate. We know it's wrong, but we don't know how wrong it is. So let's see. So the actual expected value formula, which is much less intuitive than the probability formula for this distribution, but what you're going to do is you're going to take the probability of failure and you're just going to divide it by the probability of success. And that's it. That's the entire formula. Okay? So it's a fairly easy one to calculate. It's just not necessarily one you would come up with on your own. Okay, so the actual expected value, and this is where it's a good idea to use the fractions. The fractions will make this a lot easier, because we say that's 5/6 over 1/6, which equals just 5. And that's it. So we expect to fail 5 times. So expect to fail 5 times. Again, make sure you pay attention to that, or remember that that's the number of failures. One of the most common mistakes on the geometric questions is that people will read that as you expect to succeed on the 5th time, and that's not right. You expect to fail 5 times, so you actually expect to succeed on the 6th time, not the 5th time. Okay? So there you go, and you can see, obviously, our expected value that we estimated was not even remotely close. So let's not even close. And that's because even though it seems like these numbers are getting so small over here, and we're getting smaller and smaller, and it seems like, you know, they're not really going to have that much of an impact as they get smaller and smaller, they actually are going to have a tremendous effect, obviously. Okay? And that's just because that's the nature of infinity, right? It goes on forever, so it will actually have a large impact. Okay? All right, so let's jump over to the next question. So we've got a basketball question here. So Mariah has a success rate for 72% for scoring on a free throw. What is the expected waiting time before she misses the basket on a free throw? Now this is a challenging one, even though it shouldn't seem, or it doesn't seem challenging. But there's sort of a trick to this that people mess up on all the time, and it's a very reasonable mistake to make. The problem here is that our definition of a success is not what you would assume. So a success, because we go until we succeed, and in this case she's shooting until she misses. So a success means that she misses. Okay? If she misses, that's a success. If she gets the basket, that's a failure. Okay? Which obviously is not what we are used to. So the probability of success is going to be 1 minus 0.72. Okay, so the probability of success is 0.28. And then the Q value, obviously, is that 0.72. Okay, the probability of her failing is the same as the probability of her scoring. Okay, that is a failure. All right, so with that in mind, how many times do we expect her to, or how many baskets do we expect her to make before she misses? Well, we just take that Q divided by the P, and we get 0.72 over 0.28, and it equals about 2.57. Okay? So she expects to make, so we'll do this therefore, she expects to make 2.57 baskets. Okay, and I've said this before, and I'll say it again, but remember, the expected values don't always make sense. Okay, we don't round this to 3. She doesn't expect to make 3 baskets. She doesn't expect to make 2 baskets. She expects to make 2.57. And that obviously doesn't make sense in real life, but that doesn't matter for expected value. It's strictly a theoretical value. Okay, so it's totally okay for it to be not an actual option. Okay, it's just what we expect in theory. Okay? All right, so let's take a look at a pizza question, because everybody likes pizza questions. So a very nice teacher, obviously not Mr. Hall, provides pizza for his class if they earn an A average on any test. Now the probability of the class getting an A average on one of his tests is 8%. So what is the probability that the class will earn a pizza on their 5th test? Okay, so again, The easiest mistake to make here is to look at this and say that x equals 5 because it's the fifth test. But remember, x is the number of failures, not the number of trials, okay? So x in this case is going to equal 4 because they're going to fail 4 times. They're going to not get that A 4 times before they finally do on the fifth one, okay? So our probability, well, I guess we should go through, sorry, before I'm getting ahead of myself. So our probability of success is 0.08, which puts our Q value at 0.92. Okay, remember the Q and P values always add to 1. Let's make a note of that. Always add to 1. Okay, so there we go. So we got our X, we got our P, we got our Q. So now we're just ready to use our formula. Unfortunately, this is a much nicer formula than the one from the previous distribution. So we'll just have 0.92, and that's to the power of 4 because we're going to fail 4 times. And then on the fifth trial, we have a success. Okay? So 0.06. So there is a 6% chance that on the fifth test, that is when they will succeed. Okay? So, what is the probability that the class will not earn a pizza for the first 7 tests? Now, this is an interesting question because it's kind of a trick question. You have to really pay attention to get this one. Okay? Because it doesn't say that they will succeed on the 8th test. It just says that they will fail for the first 7. So if you get a question like this, if you get a question where it doesn't specify that they're succeeding on the 8th, it's just saying that this first 7 are definitely failures, then, well, let's just see here. So what we can do is when we do the probability, we're going to do the probability of 7, but we're not going to include that probability or that p-value. So p is not needed because we're never successful. Whoops, never. Oh, can't spell. Successful. I think I spelled successful wrong too. No, I didn't. It's just illegible. Okay, so the probability of failing 7 times is 0.92 to the power of 7, but we're not going to multiply by that 0.08 because we're not saying that we're going to then succeed. Okay, so if we put that in, we're going to get 0.56. Which, since 7 is around the number of tests that most courses have, that means that we've got more than 50% chance of not getting a pizza party. All right? So, what is the expected waiting time before the class gets a pizza? So how many tests do we figure we're going to write and before we finally do get our pizza? So again, our Q values and P values are the same. We're just using expected value. And this is something you don't have to write out P and Q unless they change if it's within the multiple parts of a question. So we can just jump straight to Q over P, which gives us 0.92 over 0.08, which equals 11.5. So we expect to fail 11.5 times before we finally get a pizza party. Okay? All right, last question here. Settlers of Catan. I don't know if you guys have played this, but it is unquestionably the most boring game in the universe, and I don't recommend any of you play it, but whoops. A lot of people are big fans. Anyway, Brittany needs to roll a sum of 2 with 2 dice to get a brick thing that she needs to build a settlement. So it takes her 8 tries. On her 8th try, she finally gets it. And the question is, should she be surprised by this? that it took her that many times, okay? So first of all, let's look at the probability. So the probability of success here, our p-value, is going to be 1 out of 36, because there are 1 out of 36 ways to get a 2 when rolling 2 dice. And remember, if you can look at that chart that I gave you in the last unit at any time, or maybe it was 2 units ago, I can't remember, but it was on the on your formula sheet that you will have access to again. Okay. And so then the probability of failure here is there's 35 things that you can roll that are not 2s. So 35 out of 36. So what is our expected value? How many times do we expect to fail? So it took her 8 tries, so she had 7 failures. And if we put this in, we get 35 out of 36 divided by, whoops, oh no, that's not right. Divided by 1 out of 36, which just equals 35. So she should have failed 35 times before getting it. So should she be surprised? Yes, but not the way she was surprised. So therefore, she should be surprised. She should be surprised. It was that fast. And that's it. So it should have taken her 35 times, or 35 failures. She only had 7. So yeah, she should be super surprised. All right. And that's it for today. So until next time, go Sabres.